Okay, next up is the vision subsystem. Um, and so the vision class does extend subsystem base as part of plugging into Advantage Kit. Unlike the other subsystems, which we're going to look at, the vision subsystem is a little bit different, and the difference is intentional. Um, Typically, almost always, there is a one-to-one relationship between the subsystem class and the corresponding hardware-specific I/O object. It's a little bit different with the vision subsystem because there is exactly one vision subsystem, but there may be multiple vision I/O objects, each one corresponding to a different coprocessor. So for example, for the past couple of years, um, 3061 has had four Raspberry Pis, each with their own camera. And so therefore we'd have four Vision IO photon vision objects associated with a single vision subsystem. And the reason for that is there are some things we want to do in terms of logging and whatnot, um, in an aggregated fashion among all of the post estimates provided by the coprocessors, which is why there's a single subsystem with multiple I/O objects. So that is a little bit different than other subsystems, so I wanted to be upfront about that. Vision subsystem is all about providing pose estimates to the robot odometry class that we saw previously, um, based on the cameras installed on the robot. Um, So let's dive in. There's a lot going on here with the vision subsystem. Um, we're gonna not worry so much about the instance variables and all of that stuff, and we're gonna dive into the constructor so we can see how we create this subsystem. So much like other subsystems with Advantage Kit, when you construct the subsystem, you pass in a reference to the corresponding hardware specific IO object. Here we pass in an array of them because there may be multiple hardware specific IO objects. So we store those. We're keeping track of a bunch of other things that we're going to log about. A lot of this has to do with logging and tuning. So that's what much of this is for. So we'll see that as well. Um, like all subsystems, we do need to have like the inputs class, and it's the responsibility of the subsystem to create that. However, since we have multiple I/O objects, we have multiple input classes, and so here we're creating one for each of our I/O objects, as well as some other alerts and things like that as well. Um, all right, so let's see what else we do. We do need a reference to the April tag field layout, and we get that from the constants. Actually, let's jump into the constants right now and see what all is there. So here are the vision constants. Um, this is where we have a reference to the field layout path from last year, the maximum number of tags that are present. Um, we have this subsystem name as a string as a constant so we're consistent throughout the code using that for logging and other features. You can see that we have enable detailed logging, and that's currently set to false. We can do there's a performance hit for doing the detailed logging. So during competitions, we turn this to false. We can always turn it on for replay, and we can always turn it on if we're like actively, debugging or tuning something related to vision. We also have a feature in here that we added last year for calibrating camera transforms. We'll talk more about that later, but that has helped tremendously in terms of the accuracy of our vision pose estimates, and was critical last year in terms of aligning with the branches on the reef. Um, Lots of constants here that can be tuned um, for various things. Um, So when we have a reset pose to vision command that is run, we want to make sure that the pose it's resetting to was determined relatively recently. So it says like within the last half second. That can be adjusted. Um, we have if for some reason it took like a tenth of a second to see an April tag, then we don't log those. Um, we'll see what that means in terms of that helps with like persistence, so things aren't like flashy as much when we look at logs in advantage scope. Um, so that's the tag part. We have a similar threshold for logging poses. Um, we have a threshold here for now we get into things that actually matter in terms of the pose estimator. We have an ambiguity threshold. So we say the ambiguity has to be less than 0.5 or else we don't consider it a valid pose estimate. Um, we have to say that the maximum difference in degrees must be within plus or minus 10 degrees between the robot's current rotation as determined from the gyro and the rotation calculated from the vision. Um, this is a nice way to throw out some vision pose estimates that are clearly wrong, usually due to ambiguity because the rotation is way off. We also have a threshold for reprojection. When we do single tag, we focus on ambiguity. When we do multi-tag, we focus on the reprojection error. That has to be less than 5 or else we assume it's not a valid pose estimate. Another way of just like you just want to get rid of those vision pose estimates that are not actually correct. Another simple thing to check is we know the robot most years is on the carpet. And so we have a max C error here of 0.25 meters. If it's more than that off, then we're like, okay, clearly the robot is not, you know, 30 centimeters off the ground. So we can throw out that pose estimate. If the pose estimate is outside, it's more than half of a meter outside of the field boundary, we know it's not correct. That also gets another nice way to filter out pose estimates. We then have a calculation we do to calculate the standard deviation that is passed when we add the vision measurement to the robot odometry. And so this is different ways of scaling the various factors that contribute to the calculation of that standard deviation, which we'll see later. But ambiguity gets scaled, reprojection error gets scaled. There's coefficients here for the standard deviation for X and Y, different one for theta. And then we have some simulated stuff here. We'll look more at the standard deviation part later. Let's jump back to the vision subsystem class itself. So we log the field layout. If for some reason we generate an alert if we're not using the official April tag layout for that year, which may be the case. We may be doing our own vision tuning in a modified version of our practice field where their tags are in a different place or whatever, and that's fine. But we just want to make sure, like, if that's the case, we didn't forget to change the code back to use the official one. So this will generate an alert if we're not using the official one. We create an array of all the April tag poses. We save those and log them with Advantage Kit, and that way they will show up in the log, and we can see that as well, which is super handy. And then we grab the robot poses for calibration. Again, this is only when we're calibrating our robot to camera transforms, which we'll look at later. All right, so that's all the setup stuff. There's a lot that goes on there, but we don't really care about how long that takes because it's only when the code when the robot first boots and the code is loading. We do want to make sure that the periodic method runs as quickly as possible. So you'll see a variety of performance things that we do in here to keep this method consuming as few cycles as we can. All right, some of this is like a traditional subsystem, and we'll look at other more typical subsystems later. But we want to just keep track of, like, are we getting vision updates or not? So we set it to false at the beginning, and then if we are, that'll end up true at the end before it gets logged. We go through each of the vision IO objects, and for each one, we tell it to update its inputs. And so we pass along the inputs class corresponding to each vision IO object, and then we log all of those just like we would with any subsystem, except we do it multiple times because we might have multiple IO objects. All of this is used for logging. So all robot poses, accepted, rejected. What we mean by accepted is vision pose estimates that we determine are valid versus vision pose estimates we determine are invalid. We log both of those because we want to see what is being included and what is being excluded, especially when we're tuning things. We also log all the tags that have been seen as well. All of these are array lists, and so we clear them all here because that's a very efficient operation We purposefully use array lists so that we don't incur any memory allocations during the periodic method. We just clear out the objects that were there before and then put new ones in the same space. And they're allocated large enough to hold whatever they need to for this stuff. So the default is just fine. All right, so then we have a big loop here where we go and look at all of the different Vision IO objects, all the different cameras that are involved. And so various things that we're gonna keep track of and log with. If the camera isn't connected for some reason, that's really important for us to know. So we will actually generate an alert if that is the case. So we have that there, which is super important. Cycles with no results. We want to keep track of like how many cycles of, periodic cycles, the 20 millisecond period cycles, have we not seen any April tag with a given camera. And so we'll increment that here. And then if we have seen an April tag, we'll set that back to 0. But that helps us see in like our cameras performing as they should. Or if we look at the log file later and it's like, wow, this camera like never saw a tag. Like, well, but it was connected. Well, what's going on there? Like, oh, do you leave the camera cover on? Is it out of focus? Whatever it happens to be. All right. All of these instance variables, tag poses, camera poses, robot poses accepted and rejected. These are lists where each IO object, each camera index has their own object. So it's an array list of array lists. And so we're going to clear that out for each one. So we log everything by camera, by IO object, and we aggregate it together because usually we want to see, well, what's the effect of all the cameras on the robot? All right, so all of that is to get ready. Inside of the inputs object associated with a current camera is a list of pose observations. And so we're going to go through all of those and process those as we go. Some of this code comes from the recommendations from Photon Vision. And so Photon Vision, if I recall, encourages you to check that to keep track of the last timestamps and make sure this is actually like newer vision data. If it's not newer vision data, then just ignore it. We've already dealt with it. If we're calibrating the camera transforms, we're going to log that. We'll come back to that later. Let's not get distracted by that right now. We do store the timestamp. That's really important. We're going to add the pose estimate from the observation to our list as well. We are going to, that's the camera pose, to be clear, which we log. We then are going to convert it to a robot pose. And so the way we do that is we take the camera pose and we add to it the robot to camera transform for the specific camera. It's the inverse of that. And so that gets us our estimated robot pose for the robot based on what that camera saw. We convert it to a pose 2D as well. We want both the pose 3D and 2D, so we can use that for either 3D or 2D viewing in Advantage Scope. And so we add that to our array list of things we're going to log. We now need to determine if we're going to accept the pose or not. There's a lot of things we check, and we saw many of these referenced in the constants file. There are times we just disable the entire vision subsystem. It's more of just a safety measure, like a backup measure if things go really wrong. So we check if the vision subsystem is enabled. Assuming it is enabled, we check this instance variable called cameras to consider. We'll go on a little bit of tangent here. Cameras to consider allows us to dynamically only consider a subset of all the cameras on the robot. This was specifically valuable in 2025 with Reefscape because when approaching the reef and we were going to score a coral on the reef, we only wanted to use the cameras that were looking at the reef, and we specifically wanted to exclude the cameras looking away from the reef that may be seeing other April tags, but probably not as accurately as the ones on the reef. And so This allows us dynamically to only consider a subset of cameras. So if this camera index is within this list of cameras to consider, great, we're going to look at his pose. Otherwise, we're just ignoring it entirely. If it's multi-tag, we want to make sure the average ambiguity um, oh, I'm sorry, I said that wrong. And if it's multi-tag, then we're going to look at something else. But if it's not multi-tag, then we want to make sure that the average ambiguity is less than the ambiguity threshold. The logic here is a little bit tricky. If it's single tag, great. We would have already checked the ambiguity. But if it's not single tag, meaning it's multi-tag, then we want to make sure that the reprojection error is less than our threshold there. So all of this is about checking either reprojection or ambiguity. We want to make sure the pose is on the field. We want to make sure the pose rotations are reasonable. If all of these check out, then we're going to accept the pose. Okay. If we are accepting the pose, then what we do is we want to actually capture which tags was this vision pose estimate based on. And we can see the tag scene bitmap, which is a single numerical value, which encodes which of all the tags have been seen. So we can look at that. And if we're doing a detailed logging, then we're going to keep track of specifically when we saw each tag. And that can be helpful for doing some more detailed like debugging. But then we also add that we add which regardless we add which tag we saw for the pose estimate, and so we can see that therefore we can actually, when we're playing back the logs, we will draw lines from the robot to the various tags that we're seeing at each moment, so we can actually see which tags are in view and are being used, which is super helpful. So all of this again logging. Here is where we add the estimated robot pose to the list of accepted poses. Again, if we're doing detailed logging, we keep track of the time as well, so that we can see the poses come and go. We have a whole method to calculate the standard deviation. We'll look at that later. Here is where we actually update the robot odometry and add our vision measurement, which is the part that we actually care about. So more logging stuff then. So this is all about determining like, okay, well, what's the current best robot pose? If it's been a long time, then we're just gonna like grab one. We're gonna use the current one as our best one because we don't have any others. If not, then we're only going to replace our current best pose estimate if the one we just captured is better than that one. So you can see here where we do that based on comparing the standard deviations. So we keep track of the most recent best pose, the timestamp, and the standard deviation so we can determine that. All of this is used in terms of when we reset the robot odometry based on the vision pose estimate. Keep track of how many poses this camera has seen, so we increment that. Do a bunch of logging. We're going to log that updated pose count. We're going to log our standard deviations for the X, Y, and theta directions. All of that stuff gets logged. If we're not accepting, this is the else case for like, hey, we're not accepting this pose, then we're going to add the pose to our list of rejected poses. Again, if we're doing detailed logging, we do the time stuff as well. Regardless of whether we accepted or rejected it, we saw a tag and had a vision pose estimate. So we'll set the cycles with no results to 0. And we know the vision is updating because we got a pose estimate. So that's great. So we repeat all of that code for each observation. It is possible that in a given call to periodic for the vision subsystem, there are multiple pose observations to process from a given coprocessor. So we will process all of them. After we have processed all of them, we will log all the data specific to this camera. We log the latency. We log the cycles with no results. We log the poses of all the tags that we're seeing. We log the poses, the estimated poses of the camera itself. We log the estimated pose of the robot based on that robot to camera transform. We log the accepted robot poses, the rejected robot poses. We log the camera axes. This is a nice thing to look at. It can be tricky to get your robot to camera transforms right. And so this, by logging the camera axes, we can go into Advantage Scope and look at the 3D view and actually be like, yep, that's where our camera is. Yes, all those axes are pointing in the right direction. Um, If we're not doing this whole detailed logging thing, then we just add all of the robot poses accepted and rejected for this camera, we add to our overall lists. And all the tags seen by this camera, we add to our overall list. Okay. Um, if we're doing detailed logging, you'll see later, like we do it based on times, so it looks a little bit smoother. All right, this bracket here finishes this loop for each of the cameras. Okay, so then we repeat everything we just went through for every camera on every coprocessor. We then log our summary data. So if we are doing the detailed logging, here we use a map, and we only basically add things that have happened within the last like tenth of a second. Um, this is great for replay. It's great for looking at logs because it's like old post estimates just like go away after a tenth of a second, and you don't get the jittery and things coming and going. It's very smooth. It's very clean. But this takes time, and so we don't want this performance hit during a competition. So we only do this when this is set to true. And like I said, if it's really important that we look at the data in this way, we can always replay the log file with the set to true and then see all those details. But regardless, we're going to log all of the accepted robot poses from all of the cameras, as well, and the rejected ones, and then all the poses, whether they're accepted or rejected, they all get logged. We log all the times, whether we're doing it in the detailed way or not. They get logged. We log the April tags. We keep track of whether vision is enabled. Um, we keep track of whether vision is updating. If there's a cycle where we don't have any updates, we're not really worried about that. So we actually use a debounce here. Jump up here. Our debounce time is a tenth of a second, and the debounce type is only on falling. What that means is we're only gonna is updating is only going to go to false if we haven't seen any tags and have no vision pose estimates for a tenth of a second, which shouldn't happen. So, um, at least on modern fields, um, in the way we have our cameras. And then we also log the cameras that we're considering so that we know which cameras we are and are not looking at. And then this log tracer that we've seen elsewhere lets us know, well, how much time did we just spend in that periodic method? So that's a lot of stuff. A lot of it is related to logging. Um, Getting our vision pose estimates accurate, debugging that, tuning that is really important, um, for having a high performing robot. And so there's a lot of support here to help us do that efficiently. All right, let's see what else is in this class. Not a lot more. Here's the method to specify which cameras to consider. I referred to that earlier. So for example, as we're approaching the reef and reefscape, getting ready to score our coral, we can invoke this method with a subset of cameras, just those looking at the reef. After we score the coral, we can invoke this method again with all of the cameras, to use all of them as we go, to get the next game piece. Return whether we're enabled. Get best robot pose. This is only used with the reset pose to vision command to return, hey, here's where we think we are based on the cameras. So we do this a lot. Um, we do this a lot when just practicing on the practice field. Hey, let's get the robot so it knows where it is on the field. We can do this during a competition match if something has gone wrong and the driver feels like our odometry is off. Excuse me, it needs to be reset. We usually don't need to do that. It usually takes care of itself. Enabling and disabling the entire vision system. And then here's some of the helper methods that we saw. So determining, hey, are we on the field? meaning within the constraints of the field and not too far off the ground or below the ground. Um, Checking the pose rotations here. We just want to make sure like the vision pose estimate is reasonably close to where the robot itself is. Um, Here's how we calculate our standard deviation. So this is something that takes some tuning and different adjustments here. We have a different constants for the X and Y standard deviation as the theta standard deviation. We'll talk more about that in just a moment. But for X and Y, what we do, these are, you know, these are what we've tuned to that seem to be working well for us. Um, we use the average tag distance and we square that. In general, not in general, but tags that are closer tend to be result in more accurate vision post estimates than tags that are farther away. Um, the more tags we see, the more confident we are that the vision post estimate is accurate. So we use that as well. And then we have our factors that are specific to our robot configuration as well. Um, So there we go. That's how we calculate the X and Y standard deviation. We will adjust that though. So we also want to incorporate either reprojection or ambiguity. So if it's multi-tag, we care about reprojection. Here's that scale factor that I talked about earlier. We use that to scale the reprojection error, multiply that by the standard deviation. If it's not multi-tag, we use ambiguity. Here's the ambiguity scale factor we saw earlier. We multiply that by the average ambiguity plus 0.1. This probably warrants more of a comment here. The average ambiguity is sometimes zero. And if we multiply the X and Y standard deviation by zero, it's going to be zero. And it's great that we were that confident in the vision pose estimate, but it's probably not really that good. We don't want to have a standard deviation of zero. It's not perfect. So we always add 0.1 to our average ambiguity, just so that we make sure that our X and Y standard deviation doesn't become zero. Theta standard deviation is a little bit different. We only um, we set it to positive infinity if we just see a single tag, because we're not confident in the theta that we get out of that. We believe our gyro is going to give us a more accurate thing all by itself. However, if it's multi-tag, we're much more confident with the rotation that we get from the post estimates because two tags were seen, in which case we'll actually do a similar calculation here with average tag distance, um, the reprojection, the number of tags, standard deviation factors, all those types of things. So we calculate standard deviation as well, throw that into a vector, that's what gets returned. So this is how we currently calculate our standard deviations. We've been pretty happy with this, but always looking to make it better. The last thing I want to comment on with this class is this log camera transforms. This is an addition in 2025, which has been fantastic. Um, so again, would never be done during competition. This is only done like in the pits or on the practice field. The purpose of this is for us to, oh, wait, I misspoke. The purpose of this um, is to basically log exactly where the robot is based on the vision pose estimate. This does not have to do with robot to camera transforms. We'll get to that later. Um, so what this means is for example, we use this on the competition field during field calibration in Reefscape to um, empirically determine where the robot should be to score on each of the branches. So we would do this 24 times on the Reefscape field to get a specific pose for each of those 24 branches. So all this does is if this constant is set to true, because we don't normally want to log all this stuff. We're only doing this when we're doing field cal at a competition. We get the camera pose. Um, we transform it to the robot pose, um, and then we log both of those to the file. We would then use this log to set target poses for scoring on each of the different branches. Okay, so this is part of our field calibration procedure that we go to. So, all right. So that's the vision subsystem class. Um, because it is an Advantage Kit subsystem, there's also a Vision IO class. Okay, so this is the interface that sits at our hardware abstraction layer. It defines the Vision IO inputs class, which has a Boolean for whether the coprocessor is connected, and then an array of pose observations. Because again, there might be multiple ones that need to be processed. A pose observation has all of these things in it. Timestamps, camera pose, latency, average ambiguity, reprojection error, which tags were seen as a bitmap, the number of tags, average tag distance, and the pose observation type, which is either single or multi-tag. So that's all the stuff that we use, and it has its standard update inputs method. There are no other methods in the Vision IO class. We're just going to call update inputs. Um, we have two classes that implement the Vision IO interface. The one is the Vision IO Photon Vision. This is when we're talking to a coprocessor. So let's look at this one first. Here, when this is created inside of Robot Container, we give it the name of the camera and the April tag field layout, creates a new photon camera object. This code is very similar to that suggested in the Photon Vision documentation. We create a photon pose estimator. We are doing multi-tag PNP on the coprocessor, not on the RoboRio, to help with performance. So we do that first. We get rid of any old results that are lying around when we construct this object. The updates input method. This is very similar, just customized for Advantage Kit, to what is recommended by Photon Vision. We keep track of whether the camera is connected. That's easy to do. Clear out a list of observations. Go through all the unread results. Each result is a photon pipeline result object. From that, we get the vision estimate. By passing the result to the photon vision pose estimator. And then if there is a vision estimate, if that comes out, great. These are all the things we want to do. We basically want to fill in that everything we need in terms of that inputs object. So we see all the targets used. We build our bitmap. We use the bitmap just for efficiency reasons. We can use a single number to represent all of the April tag locations rather than having 30 Booleans or something. Calculate our average ambiguity, our average tag distance, all of that stuff. And then we make our new pose observation with all the stuff we want. And that, add that to our list there. Pose observations has to be in an array, so we do have to call the toArray method here to convert our list to an array, so that it can be logged appropriately. I think that is all of the interesting stuff. Yeah. The other subclass, or the other class that implements the Vision IO interface is the Vision IO Sim class. This is used for simulation. Again, very similar to what is recommended in the Photon Vision documentation. This is great because it allows us to simulate a photon vision system when we're just simulating a robot. So there is no Raspberry Pi, there is no camera, but yet based on where the robot is, this determines what tags it should see. And so all the code related to vision keeps on running, which is great. In order to do that, when you construct a Vision IO sim object, you need a pose supplier so that it can know where it is. And so that's why that's included here. We actually have our Vision IO sim object extend the Vision IO photon vision object because so much of the code is the same. It's just that the constructor is like a little bit different. So this just keeps us from duplicating a lot of the code. So we do have to deal with the pose supplier. You'll see where we use that in a moment. We do need to create a vision system sim object. We have to give it all the April tags. We have to make a simulated camera. Um, and then first we have to make the properties for it based on like the camera's height and width and frames per second and latency. Um, and that will move around some. The calibration error, like how accurate it's going to be, so it's not necessarily perfect. And then we create our simulated photon camera, add that to the vision sim, and we're good to go. In update inputs, all we have to do is get the current pose from the pose supplier and invoke the update method on the vision sim. So now the vision sim knows where the robot is and therefore can determine which tags should be seen. And then we can just call the superclass. So just a little bit of simulation specific code in here. All right, that's the entire vision subsystem, all focused on providing vision pose estimates and feeding those to the robot odometry.